And why do we really care about the efficiency? Going back to the basic a little bit, because we already found out kind of numerical number like the efficiencies of this program. So we kind of gauge it. We measure the efficiency of this particular function. And why do we really care about the efficiency? Because writing a working program is not good enough often. Because the program can be very inefficient. And if the program runs on a large data set, the learning time becomes a big issue, right? If you have to run this anti-analyzer that we experimented a little bit, 200 reviews works alright. How about million reviews? It will take so much time to run it, right? So in that case, you have to have a good data structure and good algorithms to do it. Sometimes a program might not be usable because of the efficiency. Imagine a transaction system of a financial company. Let's imagine just one transaction takes just 0.001 second. How about 10 transactions by 10,000 account holders? It will take 100 seconds. Means that for each account holders might have to wait like 100 seconds if there are these 10,000 account holders request transactions at the same time, right? And if you have to wait like this long time, then people will argue about this, and this company will not be able to use this particular transaction system. So the speed of the program often becomes a key problem in analyzing real-world data set. Okay, so the side effect is that there is no reaction from the system. User clicks the request again and it stacks up. Then at the end of the day, the system breaks, right? Imagine a sorting function for bank accounts. You want a certain kind of analysis on the data set. So we have, I'm working in the bank, and we have these customers, means that account holders, these many, and we have like 10,000 accounts, and I want to have from the maximum, the accounts has the maximum balance to the minimum balance. I want to sort it out. Then it means that we have roughly this many iterations for sorting. We analyzed it mathematically in the previous section, right? Then it's nonsense to execute this many iterations, right? You will not be able to report anything from this sorting analysis. So therefore, we need to guarantee a worst case scenario, right? In the worst case run time of a single transaction, worst case transaction request per numbers a single day, or worst case scenario of the sorting algorithms to run, right? How long will it take, and how long will this sorting algorithm will consume time, right? These kind of questions will really determine whether your program be usable in the real world or not. Okay, turning our example analysis a little bit more practical, and we are going to introduce a little different problem called selection problem. It's really different from the sorting problem, but it's selection problem. It means that given a list of n numbers, I want to find the case largest numbers. Means that, for example, if we have 100 numbers, I want to sort largest numbers. And it's very likely happen in the real world. We have this many investors, and I want to see the third largest investors in my database. It's perfectly alright. Frequent scenario happens in the real world, and you want to solve it. Yeah. And let's see how two analysts can solve this problem with two different approaches. One algorithm would be a complete sorting, right? If you are going to use the selection sort, perform selection sort, then these 100 numbers will be lined up in the descending orders, and you just pick the third number of the descending order. Means that it's the third largest number, right? So this algorithm would be the selection sort, and you just returns the case number, right? Case number of the list. So the efficiency of this approach will cause this many iterations, which becomes the worst case scenario iterations of the selection sort. We already explained this and we already covered this, so it's very simple, right? But it's going to take like the how many 100 multiply 100. It will take like the right 5050 and 4950 iterations also, right? So we have this many if statement runs, right? And that's going to be the problem. And another analyst come in and say that, okay, I can find out the case element much faster, and this is the algorithm the another analyst suggested. It's kind of long. Let's go through this algorithm per second. Okay. So first you have to read the case number, right? You have to not read store the case number in somewhere. And what you're going to do is that you just pick the first, right? If you have the 100 numbers here, you just pick 3, right? This k is 3, right? And you just pick 3 numbers and sort this thing, right? And this at least this part is all sorted out. So this is sorting, and it will take how many? K's plus minus k squared minus k times of the iterations, and it will take k iterations, right? And this is the fun part. So this analyst added up. Instead of sorting this 100 total, we are going to sort it the only first k numbers, and then what happens is that for the rest of these numbers, for the 97 numbers, we are going to see that these first 3 numbers, the rest of the sorted this third number is the last number being sorted, right? And if the next number is bigger than the last number of being sorted, then what happens is that we are going to put this number in somewhere this sorted list. In this sorted list. We don't care about if it is less than case number sorted. The last sorted number means the case number. We don't care, because from the pores to the nth, or like more precise, from case number to the nth number, we do not care about the order. Means that sorting this rest of the 97 would be just redundant work. We only need to sort things out for the first k numbers. And if a certain number is bigger than the last k number. We are going to put that number in the first k somewhere throughout these routines, right? It learns from the 1 to k to put it at the right place. If it is less than the case number, then we already have all k bigger numbers than the case number, which is being sorted out, right? And then we don't care about the number about that. If it is less than, if it returns false in this if statement, right? So what this for loop does is cutting the case to ends from sorting effort, right? That is happening in the third part of this algorithm. And if it is bigger, there is a possibility, a certainty that a certain number is bigger than the current case number, we are going to put that big number at a certain place. That is what is happening here, right? And to perform that, we have this operation. We had n minus k for loop here, and the outside we have k operations, right? So that is the complexity of these particular routines. And let's see what is happening here. So k is just 3, and 100 minus 2, 3 squared plus 3. And we all plus the aggregated and resulted in this short formula here. Let's do it for a second, right? K plus k squared minus k plus nk minus k squared, right? So this and this makes minus k squared nk, and that is plus. That's what we see here, right? And then the result is somewhere around 300, because that this is not that much numbers. Compared to these 300 numbers, the 4,950 number iterations are big. And that this whole difference happened when we ignored this 97 number sorting. And the third part of these operations makes this program, this algorithm much faster than the previous one. So one analyst chose a very simple way, just to do the selection sort for the whole number we have, and we will just pick the third number here, and that analyst will return the analysis result slowly. And this analyst chose a little bit complicated way, but this analyst will have a power to analyze millions of numbers rather than hundreds of numbers. So having efficient ways of performing algorithms actually expand the horizons of the analysis scope, and that is a key lessons to be learned in this part. So we really need efficient program, faster algorithms to expand our horizons of the analysis, right? And if we just choose a simple way, slow algorithm, doing the whole sorting, then the result will be slow. And because it's going to be slow, if we are going to learn the million numbers, the algorithm will never finish it. In that case, we don't have the result, and it's not a working solution. If we choose a faster, efficient way, then we can learn the million numbers. Then we might find some interesting result from the analysis. And actually, this kind of efficiencies are called upon for the real-world analysis, right? And this is a kind of simple examples how to different approaches can result in so much difference in terms of the efficiency. Okay, so far what we have done is that turning a computer program or measuring a computer program with a mathematical formula, and to see how long will it run, right? How much efficiency does that program have? And that was our kind of simple analysis, and we provided that analysis with simple examples. And we are going to formalize it more. We are going to make some notations, we are going to do some definitions, and we are going to do a little bit theorems here in the second part of this lecture, and to formally introduce algorithm analysis, right? So that's the end of the part 1 of the week 5.